World War II is often remembered as a race of innovation. Faster planes, stronger tanks, deadlier weapons. A war where technology decided who lived and who lost. But hidden behind those breakthroughs is a different story. A story of machines that looked powerful on paper, yet failed the moment they touched reality. Weapons so heavy they couldn't move, so complex they couldn't fire, so fragile they broke before reaching the enemy. And still, nations kept building them. Not one, not two, but dozens of projects that consumed resources, time, and human lives for almost no return. So the question isn't just what these weapons were. It's why anyone thought they were a good idea in the first place. By 1943, Germany was already losing the initiative on multiple fronts. Instead of simplifying production or focusing on reliability, parts of the German High Command, including Adolf Hitler, pushed for increasingly heavily armored breakthrough weapons. The idea was straightforward. Create a tank so well protected that it could survive anything, break through enemy lines, and act as a moving fortress. That concept led to the development of the Panzer VIII Maus, designed primarily by Ferdinand Porsche. Technical specifications: weight, approximately 188 tons. Armor, up to 240 millimeters. Front hull, main gun, 128 millimeters, KWK 44L/55. Secondary gun, 75 millimeters coaxial cannon. Crew, 6. Engine system, gasoline engine powering electric transmission, hybrid drive concept. On paper, the armor alone made it nearly immune to most Allied anti-tank weapons of the time. But the engineering decisions behind it created cascading failures. Mobility problem. The Maus had a top speed of around 13 kilometers per hour under ideal conditions, and often much less off-road. Its weight exceeded the load capacity of almost all European bridges. Instead of solving that, engineers proposed an alternative. The tank would cross rivers underwater, using a snorkel while receiving electrical power via cable from another Maus on land. This solution required 2 operational tanks, stable river conditions, no enemy interference. In real combat, this was impractical. Powertrain complexity. The Maus used a complex electric transmission system, similar in concept to modern diesel-electric systems, but far less reliable with 1940s technology. Result: frequent overheating, mechanical failures, extremely difficult field repairs. If the tank broke down, recovery was nearly impossible. No standard recovery vehicle could tow it. Logistics and production impact. Producing a single Maus consumed enormous amounts of steel, large quantities of copper, critical for electrical systems, specialized manufacturing capacity. At the same time, Germany was facing fuel shortages, Allied bombing of industrial infrastructure, increasing demand for simpler, mass-producible tanks like the Panzer IV and Panther tank. From a resource perspective, one Maus could have been replaced by multiple operational tanks that were faster, easier to maintain, and deployable. Operational reality: only 2 prototypes were completed. Neither was fully combat ready. One was scuttled by German forces near the end of the war. The surviving combined prototype is now displayed in Kubinka Tank Museum. Analytical conclusion: the Maus represents a classic failure of military engineering driven by flawed assumptions. 1. Overemphasis on protection over mobility. 2. Ignoring logistical constraints. 3. Technological overreach beyond industrial capability. 4. Strategic mismatch with actual battlefield conditions. Instead of adapting to a fast, resource-constrained war, the project doubled down on complexity and scale. The result was predictable. The Maus wasn't just ineffective. It diverted resources from weapons that could have actually impacted the war. It wasn't a weapon. It was a liability. If the Maus was a failure of scale, the next weapon was a failure of complexity. Germany's so-called V-weapons program, Vergeltungswaffen or weapons of retaliation, aimed to strike Allied cities from a distance. Most people know the V-2 rocket, but there was another project that pushed engineering even further, and much further away from reality. The V3 cannon. Its concept was radically different from traditional artillery. Instead of a single explosive charge firing a shell, the V3 used a multi-chamber system along a very long barrel. As the projectile traveled forward, side chambers would ignite sequentially, adding extra acceleration. In theory, this allowed extremely high muzzle velocity, ranges exceeding 150 kilometers, the ability to hit targets like London from continental Europe. The main installation site was at Mimoyeke's fortress in northern France, but the theory collapsed under real-world conditions. Engineering problems. 1. Synchronization failure. The side charges had to ignite at precisely the right moment, too early or too late, and instead of accelerating the shell, they disrupted its motion or damaged the barrel. Result: inconsistent velocity, severe accuracy issues. 2. Structural stress. The repeated detonations along the barrel created extreme internal pressures. The system was prone to cracking, deformation, catastrophic failure. 3. Barrel length and vulnerability. The V3 required barrels over 100 meters long, fixed in place at a specific angle. This created a critical weakness. It could not be relocated. It could not be concealed easily. It became a static target operational failure. Before it could become operational at scale, the Mimoyeke's site was heavily bombed by the Allies in 1944. Using tall-boy deep penetration bombs, the Royal Air Force effectively neutralized the facility. A smaller, shortened version of the V3 was later deployed in Luxembourg, but the results were minimal. Limited number of shells fired, low accuracy, negligible strategic impact, cost versus effect. The V3 required massive underground construction, precision engineering under wartime conditions, protection against air attack. In return, it delivered limited damage, no meaningful shift in the war. At the same time, Germany was losing air superiority, meaning any large fixed installation was almost guaranteed to be destroyed. Analytical conclusion. The V3 highlights a different kind of failure than the mouse. Not excess weight, but excess complexity. The project assumed that more advanced engineering equals better performance. Theoretical capability equals practical effectiveness. But it ignored key factors: reliability under combat conditions, vulnerability to air power, diminishing returns of increasingly complex systems. This is what happens when engineering ambition overtakes operational reality. The V3 wasn't just ahead of its time, it was detached from it. Not every failed weapon in World War II was massive or complex. Some were designed to be small, simple, and cost-effective, at least in theory. One of the most widely produced examples was the Goliath tracked mine, SDKFZ 302/303. The idea was straightforward. A small tracked vehicle loaded with explosives would be remotely guided toward a target, tanks, bunkers, bridges, and detonated on impact. In concept, it solved a real battlefield problem: how to destroy fortified positions without risking soldiers. Technical characteristics. Weight, approximately 370 to 430 kilograms, depending on version. Explosive payload, 60 to 100 kilograms. Speed, approximately 6 to 10 kilometers per hour. Control system, wired remote, up to approximately 650 meters cable. Propulsion, O early version, electric motors, expensive. O later version, gasoline engine, cheaper but noisier. Over 7,000 units were produced during the war. So why didn't it work? Core failure, vulnerability. The Goliath was extremely easy to neutralize. The control cable was its biggest weakness. A single bullet, shrapnel hit, or even rough terrain could sever it. Once cut, the vehicle became uncontrollable. The vehicle itself had thin armor. Rifle fire was often enough to disable it. Its slow speed made it an easy target. Infantry could spot and destroy it before it reached the objective. Operational limitations. Required line-of-sight control. Operator had to remain relatively exposed. Difficult to use in urban rubble, forests, uneven terrain. In real combat, conditions were rarely ideal. Cost inefficiency. Despite being considered a cheap weapon, the Goliath was not cheap relative to its effect. Early electric versions required valuable materials like copper. Production still consumed industrial resources Germany could not easily spare. Each use was one time only. The vehicle was destroyed upon detonation. Compared to alternatives, a soldier with explosives, standard artillery, anti-tank weapons, the cost-to-effect ratio was poor. Field results: the Goliath saw action on both eastern and western fronts, but reports consistently showed low success rates, high loss before reaching targets, minimal strategic impact. It was more effective in controlled demolition scenarios than in active combat. Analytical conclusion: the Goliath represents a different type of failure, not over-engineering, not excessive scale, but a misjudgment of battlefield reality. The designers assumed remote control would reduce risk, small size would increase survivability, simplicity would ensure effectiveness. In reality, communication systems were fragile, the battlefield was chaotic and unpredictable. Low durability negated any theoretical advantage. This is what happens when a weapon is optimized for a perfect scenario, one that doesn't exist in real war. A cheap idea. That still failed. Some weapons fail because they're too big. Some fail because they're too complex. And then there are those we still don't fully understand. The kugelpanzer is one of them. Only one known example has ever been found. It was captured by Soviet forces in Manchuria in 1945, likely at a Japanese-controlled facility. Today, it sits in the Kubinka Tank Museum, and even now, its purpose remains unclear. What we actually know: structure: spherical armored body with two large wheels forming the sides. Armor thickness: approximately 5 millimeters, extremely thin. Crew: likely one person. Entry: rear hatch. Vision: narrow viewing slit at the front. Propulsion: small internal engine driving the wheels. There is no confirmed main weapon system, which immediately raises the core question: what was it for? Hypotheses: 1. Reconnaissance vehicle. Small size, low profile. But extremely limited visibility and protection. 2. Observation or artillery spotting platform. Could move slowly and relay positions. But communication equipment would have been limited. 3. Suicide or demolition device. Similar in concept to the Goliath, but no hard evidence confirms this. 4. Psychological or experimental prototype. Testing alternative mobility concepts. Not intended for mass production. Critical weaknesses: armor too thin to survive even small arms fire. Mobility extremely limited. Uneven terrain would be a major obstacle. Visibility poor, making navigation difficult. No clear combat role. Unlike the Maus or V3, which failed despite clear intentions, the Kugelpanzer represents something more unusual: a machine without a defined operational purpose. Strategic context: by 1944 to 1945, Germany and Japan were both facing severe pressure. Shrinking industrial capacity, resource shortages, deteriorating battlefield conditions. In such environments, experimental projects often accelerate, not because they are practical, but because decision-making becomes fragmented. Different teams pursue ideas independently. Prototypes are built before roles are fully defined. And some concepts move forward simply because they can be built, not because they should be. Analytical conclusion: the Kugelpanzer highlights a rarely discussed failure mode in wartime innovation: development without doctrine. A weapon is not just a machine. It requires a defined role, integration into strategy, compatibility with real conditions. Without that, even a functioning design becomes meaningless. The Kugelpanzer wasn't just ineffective. It may never have had a purpose to begin with. By the later years of World War II, especially after 1943, Germany's strategic position was deteriorating rapidly. The Eastern Front was collapsing under Soviet pressure. The Western Allies had secured air superiority, and industrial production was under constant bombardment. In this environment, the logic behind weapons development shifted. Instead of prioritizing reliability, scalability, and logistics, Decision-making increasingly favored high-risk, high-impact concepts that promised a potential breakthrough, even if the probability of success was low. This is the context in which projects like the Panzer VIII Maus, the V3 cannon, and systems like the Goliath tracked mine were developed. These were not isolated engineering mistakes. They were symptoms of a broader systemic shift driven by pressure, fragmentation, and unrealistic expectations. One of the primary drivers was desperation. As conventional strategies failed, leadership became more willing to approve unconventional and extreme solutions. Standard tanks were no longer stopping Allied advances effectively, so the response was to build something that could not be easily destroyed, even if it sacrificed mobility and deployability. Long-range artillery systems like the V3 reflected a similar logic. If battlefield control is lost, strike deep into enemy territory. These decisions prioritized theoretical impact over operational feasibility. Another factor was the concept of Wunderwaffen, or miracle weapons. The partial success of systems like the V2 rocket reinforced the belief that a single technological breakthrough could alter the course of the war. This belief persisted even when other projects consistently failed. The expectation of a future decisive weapon justified continued investment in experimental systems, diverting resources from proven platforms. This created a feedback loop where failure did not reduce confidence, it increased the urgency to find the next breakthrough. At the same time, the German military-industrial system suffered from structural fragmentation. Competing organizations, design bureaus, and influential individuals pursued parallel projects. Engineers such as Ferdinand Porsche promoted ambitious designs not only for military reasons, but also to secure political support and industrial priority. Without strict central coordination, multiple projects advanced simultaneously, often without clear strategic integration. This resulted in redundancy, inefficiency, and the allocation of critical resources to systems that had no realistic path to deployment. There was also a strong element of technological overconfidence. The assumption that more advanced or complex systems would automatically outperform simpler ones proved repeatedly incorrect. In practice, World War II favored weapons that could be produced in large numbers, maintained easily, and deployed under varied conditions. Tanks like the Panzer IV and Allied equivalents succeeded not because they were the most advanced, but because they were reliable and available at scale. In contrast, experimental systems required specialized maintenance, rare materials, and ideal conditions that rarely existed in actual combat. Finally, these projects had a propaganda and psychological dimension. As the war situation worsened, the German leadership needed to maintain both domestic morale and the perception of strength. Announcements, rumors, and expectations around advanced weapons played a role in sustaining belief that the situation could still be reversed. Even if a weapon was not operational, the idea that it might soon be deployed had value. This blurred the line between military necessity and political messaging. Taken together, these factors explain why such weapons were built despite their obvious limitations. They were not the result of isolated poor decisions, but of a system operating under extreme stress, where normal constraints were weakened and the threshold for risk was significantly lowered. These weapons were not built because they worked. They were built because decision-makers believed that, under the right conditions, they might. In war, failure carries a cost measured in resources, time, and lives. But not all failures are accidental. Some are the result of decisions made when pressure overrides judgment and when belief in a solution becomes stronger than the evidence against it. So the real question is not just whether these weapons were useless, it's whether the people behind them understood that and chose to proceed anyway.